All right, so today we're gonna finally implement a split plot design analysis using the same data that we've been working with. Last class, the last thing that we did was to create that RStudio project through GitHub. We're starting on GitHub and then bringing that to our local files and then just starting everything. We did a git pull on the class GitHub as well to get the script. So all that we finished already. So if you can navigate to the class folder, and we're gonna start off with that project, which should be the 05 SBP. Please go ahead and launch that rproj on your side. Remember always to launch it through the rproj, not directly clicking on scripts. Let me launch the code here, and then we'll get going. Okay, so the goal of this exercise, which we're going to finish today, is going to be to create an analytical workflow for a split plot RCBD with random blocks, starting from importing the data, doing EDA, wrangling, running the model, checking assumptions, extracting model parameters, and then finally exporting something to file like a publication-ready figure. And then also through that process, we're going to talk more about each one of the components of this analysis, especially those that are a little bit different for this split plot case. I left you here all the packages for you to load. We should already have all these packages, so shouldn't there be an issue if you just want to go ahead and run that chunk. And again, I'm going to be very repetitive, but I always want to remind you that we are using the same data and playing around with different designs. As far as experimental design analysis goes, you would not do this, right? You would plan your design, collect your data according to that design, and use that model to analyze that data. So we wouldn't be playing with things. But here, for teaching purposes, we are playing around with the same data so you can see how the progression of how things progressively get more complicated, starting from CRD all the way to a split plot. All right, so I think I left you here the code for data import as well. It's been the same data as we just talked about, so make sure you import it. For some reason on my side, oh, I think I forgot to actually move the data in here. So let me do that. Yeah, so I guess, always good to have some live errors going on. So I tried to read it, and then he said that this does not exist, right? This does not exist in current folder. So basically, if I go to my data folder, it's not there. So I, on my side, forgot to copy this data here. So I'm going to do that on my side. I think probably you have already done this, so you wouldn't need to redo this step. Now this should work. Okay, so we import the data frame. It's the same as we've been using, so 36 rows. If you remember, we have 36 plots or experimental units. Notice something that, for you to kind of keep in mind is, even though we're going to be now analyzing this as a split plot design, which we went through that in lecture, and you saw what were the constraints of the field size, what were the constraints of equipment, applying one treatment at a larger area and another one at a smaller one. Now we still have 36 experimental units. The difference is that now there's going to be a structure on that. And really, that's going to reflect on the model, right? So the data did not really change. It would still be the same 36 experimental units. It's just that those would be the experimental units at the level of the split plot, right? If we were to talk about the whole plot, is going to be a different. I mean, it doesn't reflect on the data frame itself. It just reflects on the model, the actual whole plot experimental unit size. We do some always do some EDA, and this is something I also try to stress to you all. I know that so my goal with showing you these workflows is that you have some guidelines to how to analyze your own data. So I always urge my own students in my lab to do EDA. If they come to me and say, hey, I'm doing this, it's not working, and I ask, well, what's the minimum, what's the maximum, what's the mean? Did you have any error on your data entry? Did you have any weird data values? So always do EDA on your side. This is not just something that I'm putting here for no reason. There is actually a good reason for you to be looking into EDA. So, I mean, we've seen this before, yield varying from about 3,000 to about 7,000 kilos per hectare. Nothing seems wrong there. We look at Glimpse. We check that how R is interpreting our variables. Again, this is going to be very important. And our next exercise is going to be a regression exercise. And you're going to be able to see one of the differences between running a study as an ANOVA or as a regression if your explanatory variables actually have numerical levels, like in our case, nitrogen potassium rate. Today, and we've been through up until now, we have not run regression, we've run analysis of variance, in which case our explanatory variables have to be factor or categorical. Right now, R is not seeing that, and also our block or rep needs to also be factor. R is not seeing that. So we're just changing that on the chunk below. We've already done this before, so this should not be nothing new to you, but always keep in mind that this step here is required if you're doing ANOVA. You want to make sure that R is interpreting your variables correctly, because if it's not and you don't fix it, then you get results that are not what you're looking for. I actually had a typo on this chunk. You know what? Can somebody help me? It's like, what's going on here? How would you, I guess maybe we can talk about what is going on in this chunk. Okay, so block is not found. Now, what does that, I mean, how would you fix it, I guess? Yeah. Rep, right? So thanks everyone. This is really great. It was not on purpose, but I'm glad that I'm making some errors on my code so we can kind of walk through how we would fix it, right? So we look at the error message, it says object block not found. If we just print the incoming data set, we see that the column is actually called rep instead of block. So we just change rep both before and after the equal sign, and then that should work. All right, I just get another summary just because now we changed some of the variables just so we can see rep and rate, potassium rate have been changed to factor. We don't get a statistical summary for them anymore. And so that's what we were looking for. After doing those tables, we always do our EDA plots, which again, they have not changed. It's still the same data, so we're not going to spend a whole lot of time here. I just, in preparation for your exam, I just want you to know that you will be asked to interpret some plots. So if you are having trouble interpreting these plots, you have to either let me know or study on your side. But this is just, in this case here, again, we cannot really say for sure there's no difference, or even if there seemed to be a difference, we wouldn't be able to say for sure there is a difference because we're not using any statistical summary at this point. It's just EDA, right? It's just raw data being plotted. But just be aware of that. All right, so not a lot of, doesn't seem like there's a lot of effect of potassium, doesn't seem like there's a lot of effect of nitrogen. Although it seems like there's an interaction. We've talked a lot about this already, especially plots like these. You should be able to describe what's going on in an exam because that question will be there. Maybe not for this data set, but a question similar to this will be there. All right, so we're going to be running today a mixed effect model. That is because our model is going to have fixed effects, which most of the time are related to your treatment design variables. So potassium and nitrogen and interaction is fixed effect because we want to know about their means. That's our interest. And is also going to have, well, perhaps more than one random effect, but the way that we code it, it looks like just one random effect, which is going to be related to block and how we define the structure of the split plots inside the block. Again, if you're running just fixed effect model with just one source of error or variation, you use the function LM. If you're running a random or a mixed effect model, which has two or more sources of error or variation, then you use function LMER. At least that's the one that we'll be using until now. So today, because we're running a mixed effect model, we're going to be using function LMER. And here, in the case of the split plot in a randomized complete block design, we're going to have two random variance components. One's going to be associated with the whole plot error, and the other one with the split plot error. So we have two levels of error going on here. As always, I ask you to change the default matrix restrictions from sum to 0 or from set to 0 to sum to 0. This is how you would do it. And again, this does not have a direct effect on means, but it will have an effect on how your ANOVA looks like, and therefore the p-values of that ANOVA. So we always check the ANOVA to decide how we move forward with means. So always make sure you change this when you're running ANOVA models. All right, so the next step here we're going to code together because that is going to be the difference, or there's going to be one difference here between what we've been doing up until now, and how this is going to change for this split plot case. So let's give it the assignment symbol. Again, we're going to use function LMER because we have in this case here, a mixed effect model. I'm just going to print our data. So our data was, let me just pull the name of the data frame here, SPP RCBD DFW, just so we get the variable names more easily. So our formula is going to be yield explained by, we can start off with our fixed effect models just to organize things in a way that we've been familiar with. So okay, this is a great question to see if you're following along or if you're just copying what I tell you. How would you specify here the fixed effect part of this model? If you want to take a quick second to think about it, I'm going to ask Madeline. What do you think?
You just put the fixed effects.
Well, can you tell me how you would specify that in code?
The K rate.
Okay, so K rate, and then what goes in between the K rate and the N rate? A plus, okay. So we can do that. We can do a plus. And then, is there something else?
For the interaction, you also want to do the interaction term U plus and then K rate times.
Okay, so let me just break this down. So actually, if we want to do individually, it would be main effect of K rate plus main effect of nitrogen rate plus the interaction, and the interaction alone we specify with the colon, right? However, all this can basically be summarized by this, right? So this is a syntax difference that you need to be aware as well. So remember this part. Okay, so this basically sets up our fixed effect part of our model. Now I want to specify the random effect part of our model. So we had a plus there. Can someone help me to remember how so if we for 1 second forget that we're coding for a split plot and we just assume that we're doing the random blocks RCBD like we did last time, how would we specify that random effect here? So in other words, how we would specify the random effect of block by itself?
One vertical bar rep.
Okay, one vertical bar rep, right? Was that, was that Shakir?
Yeah.
Yeah, thanks, Shakir.
Mhm.
All right, yes, so this is how the model looked like when we had a just randomized complete block design with blocks random and our treatments, potassium and nitrogen, were at the same level. They were not at a hierarchy like they are in the split plots. So this is the model for a two-way treatment design, all crossed with blocks random. Now, how do we then differentiate that from a split plot? That is basically going to come down here to how we treat our random effect. On the split plot, we have to basically nest our whole plot treatment factor inside of block, or in this case, rep, how we're calling it. So what that means is you would take potassium rate kilograms per hectare. To nest one thing inside the other, you basically come here and use a forward slash and just type potassium rate. So what this means is that we are nesting potassium rate inside of rep. It's not I know that it can be a little bit confusing because if you've been using SAS, the way you specify is flipped. You first say what's the smallest and then the largest. Here we say what's the largest, which is rep. And then after that, we specify what's the next smallest level, which is potassium rate. So let's think about it just a quick second here. So this is the model that you're going to run for our potassium by nitrogen rate split plot, where potassium is the whole plot treatment factor, nitrogen is the split plot treatment factor, and we're running this on a randomized complete block design with blocks treated as random. Now, I want to just bring up something that is not what we're doing, but I want to see if you're thinking along here. So let's say if we also had, you don't have to copy if you don't want, I'm just going to copy so I don't get you confused on the code. So let's say that I also had a potassium. So we have we have potassium and nitrogen. Let's say I also had phosphorus. So if I had a P rate kilograms per hectare, that was in a split plot. So the whole plot is potassium, the split plot is nitrogen, and the split plot would be phosphorus. So it would be an even smaller size of experimental unit. It may be difficult for you to imagine since I did not show you a figure for this, but if you can imagine that there is this extra level of structure where now phosphorus is even in a smaller experimental units than even nitrogen. How do you think that you would change this model here, assuming this is a split plot design in a randomized complete block design with blocks random? Yes.
Would you do another forward slash nest P rate inside of K rate?
Okay, so Jonathan said, would you do another forward slash on the random and nest P rate? Is that what you said?
Yes.
Okay, so you're close, but not quite there. Any other guesses?
Which N rate, red rate?
Yes, so we would, instead of saying P rate here, it would be N rate, right? So you kind of think of like, so you have the block, inside of the block, you have the whole plot units, then you have the split plot units, and then you have the split plot units, right? So you basically leave the smallest size out of this. So in this case, in this split plot example that I'm making up here, the smallest size is the P rate. So we don't specify P rate in our random effect.
Why do you leave the smallest size?
Because then the error associated with that smallest size goes to your residual error. So all of this is going to be explained by your random effects. I mean, basically everything so coming back to our example here, original. All this is going to be explained about with the variance of our random effects, and the smallest size goes to your residual error, which is that EIJ at the end. So if you remember from the model, on the mixed effect model, we have our random effects and we have our residual error. Random effects are going to be what we are telling here on the one vertical bar. Whatever is left goes to your residual. So basically, every time that you have a nested structure, your smallest unit, you don't specify on the random because you want to let it go to your residual variance. Yeah, so there's a lot of ways that this nesting can happen. So if you have subsampling, for example, and you don't want to take the average of your subsamples before modeling, you would also use this nesting to create the structure so the model knows where is your true level of replication and not consider your subsampling. But we're not doing that. I know that I diverge in a few different ways here. Maybe I lost some of you on the way, but I just wanted to kind of expand our thinking here. So let me delete.
Dr. Bastos,
Yes.
what if we have like 2 time points, like 2 yield collections at different times?
Yeah, so Selvin is asking, what if we had 2 yield collection times? So that would be repeated measure. It's something that I taught it last year. So we have the code, I have the videos and everything for repeated measure analysis. I decided to leave it out this year just so we can have more time for machine learning. If people are interested in repeated measure, you can maybe let me know on GitHub issues and I can provide some materials for you to follow and learn. But basically, so Selvin, this is a great question. And I want to give you an answer, but not a full answer because that would take some time. It's probably another 2-hour class just to talk about repeated measure. But the main difference here between split, because sometimes some people call repeated measures split plot in time or space. And I mean, if this is not making sense to you, I don't want to confuse you, but just to let you know, the main difference here between a repeated measure, which is when you sample the same experimental unit multiple times, so multiple, times over time, or maybe multiple different dimensions in space. So a good example here would be if you work with alfalfa, for example, which is a forage crop that you harvest multiple times, right? So corn, wheat, we harvest once at the end. Maybe alfalfa you harvest 4 or 5 times in the growing season. And and of course, how much the plant produced today and you harvest it is going to have an impact on how much good it's going to produce on the next time. So those things are correlated. With repeated measure, in this case, that on the alfalfa example over time, but in space would be soil samples. So let's say if you take a soil sample and you take 2 different depths, 0 to 5 and 5 to 10 centimeters. What happens is that both the space and time cannot be randomized. You cannot say, I'm going to first sample the 10 days after planting, or let's say, let me make up a number that makes more sense. Let's say that you harvest like 1 month after planting, and then you harvest again 2 months after planting. You cannot say that you're going to first harvest 2 months and then 1 month. It makes no sense, right? Time is linear. You cannot randomize time. The same with space. If you take a soil sample in 2 different depths, you cannot say that you're going to first take the 5 to 10 and then the 0 to 5. They're connected, right? There is a linearity in it. So because on repeated measures is when time or space or both are involved, and the problem is that time and space are not randomizable. So we have to do a full repeated measure analysis to understand that correlation over time or space. I think that's the extent I want to go into that direction. But the main difference between that and a split plot is that a split plot can actually, all the factors in a split plot can be randomized. And they are randomized, right? We randomize nitrogen, we randomize potassium. So that's the main difference there, is being able to randomize or not. Yes, Comfort.
Yeah, you mentioned something about true replicates and subsamples. I'm not very clear on that. And I also have a question with regards to the example I shared the last time. Say, for example, for my temperature and cultivar, I had 5 different pots of the same cultivar regarded as replication. Do I also consider those as random effects aside from the fact that I have the block which is in time, like repeated experimental runs?
So Comfort, I guess so your first question was, can you repeat just the first part, please?
The subsample and the true replicate parts that you talked about.
So it may be a little bit difficult for us to visualize just because we do not have subsample in this case. But if we did, so let's say that we had for each experimental unit, we had maybe 2 or 3 values for yield. The issue is that those 3 observations that we collected in one experimental unit are not independent because again, they belong to the same experimental unit. And so they would be considered as subsampling. And then we would need to have another column in this data frame to identify the subsampling structure. And then we will use that column in the error structure of the model to make sure that the model does not inflate the total degrees of freedom and therefore the error degrees of freedom as well. Right? Because you could, if you sample, let's say 3 plants per plot, then basically you have 36 times 3. That's the number of observations you would have. Although we only have 36 independent observations, right? Because 36 experimental units. So subsampling, we have to be careful to not allow it to inflate our error, because then you're just breaking the assumptions, right? We're just saying that we have all these degrees of freedom, where in fact only 36 of them are fully independent and therefore should be going towards the error degrees of freedom. And on the other case of your specific design, I think I can follow up with you on that, or maybe we can have a chat later, just because I don't want to bring like one very specific example, for the whole class, because maybe I'm going to lose some students. But I'll be glad to connect with you later, and we can discuss in more details your specific case if you wish.
Dr. Bestos,
Yes.
I have a very brief question. So you mentioned that for split plot, we will mention the model as 1 vertical bar rep, which is the whole plot factor, then slash potassium rate, which is the split plot factor, and then slash the factor, which is the split plot, or the other one.
So let's say I guess I still have the code here. So if we had a split plot design with potassium as the whole plot, nitrogen split plot, and phosphorus as split plot, the error would be the rep, which is the largest size of replication. And then we would nest the whole plot in block. So the whole plot treatment factor is potassium, and then nest this split plot treatment in the whole plot treatment. So overall, you're nesting the split plot treatment in the whole plot treatment in the block. You will leave out the smallest unit, which in this fictitious example would be phosphorus rate.
Got it. Thank you.
Awesome.
So you're still going largest, you're not going to smallest, but you're going to large to small, leaving out the small.
Right, exactly. So we always start with the largest, which is the block, and then you start decreasing your size and leaving the smallest out. So that goes to your error. Yes.
And just to make sure, for the first model, is the end rate the smallest unit in that case? And that's why it's being left out?
Yes, so for our original, sorry, I know that I've diverged a lot and we had some great questions as well. So I'm just going to delete this, but Madeline was just asking on our original model, right? So on our original model, we have so this would be a split plot, right? So if you have a split plot, that means you have a whole plot treatment factor and a split plot treatment factor, right? And then, I mean, this idea in this design can really go deep in this structure. Like you can have a split plot design, right? Is like the more treatment factors inside other treatment factors you add, the more complexity you have in the split plot. But the idea is always that you have your largest level of replication, which is your block, and then you're going to nest from that smallest consecutively to the smaller one and leaving the last one out. So the variance associated with that goes to your residual error, the EIJ of the model. All right. So let's just finish this code here. We still need to give the data. So data equals that SPP RCBD DFW. And once we have that, we should be able to just run without any issues. All right, so the model went through. Let's take a look at the summary. So if you remember, I told you already that the summary is going to show you the coefficients of the model, which for an ANOVA, they're not very interpretable, right? So if you look here into, these are the estimated coefficients of the model. And when we ask for means, these coefficients are just combined in different ways to create the means that we want. So really, I don't really look much on the fixed effects part of the summary function. But what I want to show you here is, again, we're using restricted maximum likelihood, so REML, to fit our to fit our model, but especially related to our random effects. That's the desired method we want to use. Now, if we look into random effects, we have a couple of things here, right? So before, when we just had the RCBD blocks random, we just had rep and then residual. Now we also have potassium rate, so the interaction between potassium rate and rep. And I just want to remind you here that this is basically coming from your random effects. This is your model residual, right? So this is your EIJ. This is your sigma square block and sigma square potassium by block. So we're seeing here that we're basically partitioning the variance between our random effects and our residual. And this is structure that we're defining the model is what's going to make sure that we have the appropriate degrees of freedom of the denominator on our mean squares, or sorry, on our F ratios, which is what we want to make sure that our model is actually running what it's supposed to do. Yeah.
You said all the P rate would go to the residual. So how would that change this kind of graphic that we did?
So if we had, oops, sorry, I clicked. Oh. So here, if we had the split plot example, then we would have another, well, in our case, it would be nitrogen rate, potassium rate, and rep. There would be another line here. And this is, so every time that we do nesting like this, really what this breaks into is the main effect of the largest piece. So I just want to make to explain. So this behind the scenes is basically the same as 1 rep plus 1 rep K rate kilograms per hectare. So this basically is just a shorter way of saying this. We're showing you when the main effect of rep, and then the effect of potassium depends on rep. Potassium does not get a main effect on the random side of the model by itself because it's dependent on the rep. So that's why we get these two lines right here. We get the potassium by rep and the rep by itself. All right, let me just delete this. Yeah, so I guess just, something that I wanted to bring your attention is that now we have the residual, the EIJ, and then we have the error associated with rep or the random effect associated with rep by itself and the interaction of rep and potassium rate, which is the whole plot treatment factor that we have that structure in the split plot. All right. So if we go to our ANOVA table, you can go ahead and run it. As always, in our well, I can say for I don't remember how SAS works, but in the ANOVA table is going to show you your fixed effects, right? So we're not really seeing directly here an ANOVA table for random effects. Although there is a function from the LME4 package that you can get like an ANOVA table for random effects, but I'm not going to get into that since our interest here is on the fixed effect part of the model and getting our means. I know we talked about like this, the DF column here, degrees of freedom, is for the numerator, right? So basically the numerator degrees of freedom is always going to be how many levels you have for that minus 1. So we have 3 levels of potassium rate, 3 minus 1 equals 2. We have 3 levels for nitrogen rate, 3 minus 1 equals 2. And then the interaction is just the multiplication of those two there. This is how many degrees of freedom are being consumed to estimate these model parameters here. And that's why we have that. However, if you remember, I told you that for you to check that your model, especially split plots or other nested designs, for you to check that your model is doing the correct thing, we need to look for the denominator degrees of freedom instead. Let me see. So this function here is not showing us. Let me quickly check another function, because I know there's a couple ways to get that. And I guess I did not incorporate that directly into my code. Okay, this is also not giving us that. Well, I'm going to look into that and just get back to you later, but I believe maybe we have to, there's another function here that we use that will give us the denominator degrees of freedom, in which case, if we compare that, we would have, so imagine you would have another column here for DF denominator. We would have less degrees of freedom on potassium rates and more degrees of freedom on nitrogen and the interaction between nitrogen and potassium. Because again, potassium rate is at the whole plot level. Its error has fewer degrees of freedom. Therefore, if you remember, the error is what we use to test the F ratio of potassium or nitrogen or the interaction. So meaning that the denominator degrees of freedom is basically the degrees of freedom of the error that is testing that part of your fixed effect. So for potassium rate, the error of potassium rate has fewer degrees of freedom than the error of nitrogen or the interaction. And there's a way to check that. And again, I'll follow up with you on that to give you how to check, but it's a really important step. Okay, so again, for this data set, at least the same conclusion, right? So we don't have a main effect of potassium or nitrogen, but the interaction is significant. And therefore, because the interaction is significant, that's how we decide how we break down our means and how we get pairwise comparisons. Please remember this, because I think some of you did not get this point straight out on one of the assignments. So this is key, right? This is how we determine how we extract the means, is by looking at your ANOVA table p-values. All right, so we ran our model here. We checked our ANOVA table to see what was significant. Now, before we go ahead and use this model to get means and pairwise comparisons, we always need to check for model assumptions. Remember that. That's always a key step. So here, we're going to first extract the model residuals. And I think, let's see, we're going to do that in 2 different ways. So if you remember, every time you have something in your model specification that says, like that something is distributed IIDN with a mean of 0 and a variance of sigma square something, that means you have assumptions associated with that. That little sentence is saying these are the assumptions of this model. We have to check for it. If you remember, if you go back to the lecture, we have that specification for both the random effects and the residual. Therefore, we have to check some assumptions or all of them for the random effects and the residuals as well. So first, I'm just leaving you here the code for us to check or for us to extract the residuals of the model. So notice that we're getting the EIJs of this model basically. So if you run this piece of chunk, we're using that function called augment and then calculating our studentized residuals. If you remember, the function augment takes your own data set and just adds some more columns associated with residual metrics, which is really cool because even though we have not used much yet, but if you wanted, you could color things according to block, to potassium, to nitrogen, or maybe plot differently according to those columns to give you more indication of if you have a lack of assumptions being met, Is it coming from a specific block? Is it coming from a specific potassium or nitrogen or so on? So we could, that's why it's very useful to use this function augment, because then you have not only the residuals, but also what are the observations associated with those residuals. So you can inspect more if you want. Okay, something very important is that, again, we've been talking about these four assumptions. I think last year I talked in a more depth in the CRD lecture, which I did not, that was part of a extra credit assignment. We're still talking about these assumptions anyways, but I just want to make sure that you're familiar with them, you know what they are, you know how to test for, or how to plot them and visually assess them, because that is also a really good exam question. All right, so the four things we're checking here is independence. So we want to see no patterns. We're checking variance homogeneity, meaning that is also somewhat related to seeing a pattern, but a very specific pattern. So most of the times when you do not have variance homogeneity, you're going to see this fan-shaped effect of your residuals on the plot that we're going to have next. That is a very common way, or a very common form that lack of homogeneity appears in the residuals. We're going to check for normality using a couple of different plots, the QQ plot and the density plot as well, and then do an outlier detection. And really all of these, for all of these four assumptions, the only one that we really need the standardized residual of some sort is the outlier. Everything else is, we don't really, although we've been using the standardized studentized residual for everything, for consistency, but really the only one that requires it is the outlier detection. And we talked about this in a lecture already. All right, so again, something we talked already about last exercise is that one of the differences here is we have the random effects, and therefore there are assumptions associated with them. We also have to check. So the assumption here is that the block random effects are independently, identically distributed normal with mean 0 and variance A. So we're going to check those assumptions as well. To extract the residuals from the random effects, if you want to start coding with me, we're going to use another function. It's called runF for random effects. We just give the model here. So the model name is SPP underscore RCBD underscore mix underscore mod. And then if you run that and you just print randef block, you're going to see there is a first component that is for the interaction between the whole plot and the rep. And there is a second component that is just the rep. For us to separate these things and look at them separately, I just want to come here, do a $, and just ask for the rep, which returns those four for us. All right, so because we only have 4 reps, and this is an issue that we had before as well, we only have 4 reps, so it's really difficult to say if the assumptions are met or not for something with only 4 data points to go off of. But we're gonna make a QQ plot for these 4 data points. I left you all the code, I believe, so if you try to run it, it should just work. If you remember, the QQ plot has that solid line, which is if your data is, if your residuals are normally distributed, you would see them very close to that black line, and then we can kind of compare where they fall. I mean, you know, again, only 4 points, nothing is like extremely bad. There's no point that's really way above or way below. So we don't have a lot of data to go off of, but I would say we're meeting those assumptions for the block. Yes.
Dr. Vassos, can you please go back to that runF block thing? I think I missed something.
Yeah, so you may have missed the $ rep.
Oh, yes, yes.
Yeah. All right.
Thank you.
Yeah. Okay, so this is basically the only way that we're checking assumptions for the random effect of block. And then we're going to check the same for the random effect of block and potassium rate. So if you come here, we're going to basically use the same function. So runF Our model again is SPP underscore RCBD underscore mix underscore mod. We're gonna use that $ again. Well, let me first delete the $ and just print it. Because you're gonna have to basically copy this with those quotation marks or bracket, but I'm not sure how that's called, but just like that. All right, so that basically then creates a residual for us for each combination of block and potassium rate, as you can see here. Now I left you, if you go to the next chunk, I left you all the code there as well. So you can go ahead and run that. So, something that we saw, I guess, on the data frame, but now we can visually inspect it is, well, first, again, I don't think there is anything that worries me too much here. Normally the tails are going to be a little bit off, which they are here, but they're not too bad. But, something that I want to ask you and see how you're thinking about this. So this is a random effect. This is a random effect. So why here we have 4 and here we have what? 12. Both of those are random effects. They're not the residual. So we have still 36 residuals that we're going to inspect. But so we have 2 levels of error. One of them has 4 pieces of information. The other has 12. Why? Okay, so we have 4 blocks. So we have 4 data points for that, the residuals of that variance. And then we have 12 for the whole plot, because that is basically the whole plot nested in block, right? So we have 4 levels of whole plot, which is potassium. Or I'm sorry, we have 3 levels of potassium and 4 levels of block. That leaves us with 12 rows here. Awesome. All right, so we checked, we've just did a QQ plot on the random effect of block and on the random effect of potassium and block on that interaction, which basically together for us just means that potassium is nested in block. And before we go to the next, to check now our residual, the EIJ, Pratiksha has a question. Yes, Pratiksha.
Hi, Dr. Vestos. I just wanted to ask, like last time when we performed RCBD partial, like mixed partial model, we used double square blocks and we added 1 in that instead of $rep for random effects. How is that different?
Yes, so what Pratiksha is asking is, so the previous exercise, instead of using the $, we use the double bracket to pull different components. I have not tried here, but I would assume it's just the same, right? So I'm just gonna rerun here to get so the first, if I do a bracket 1, it should pull out these numbers. Well, we can try that. Yeah, so it's basically the same. It's just that one of them is specifying by the name, the other one is specifying by the position, but they basically give the same results. Awesome, thanks, Pratiksha. All right, so we checked some assumptions for our random effect part of the model. Now we still have to check the assumptions of the residual of the model, EIJK, which we already extracted when we did the augment. I'm just leaving here the code. It's the same as before. It's going to look very similar to before because we're mostly impacting the variance components of the model and not necessarily the means. So the residuals here, at least the way that we're showing, they're associated mostly with the actual mean that's being explained by different parts of the model. The error plays a role, but it's not a major role. So because of that, we're seeing that still the way that it looks is similar to before. There's some differences, but not very distinct. So here again, I mean, it looks like there is somewhat of a pattern but because this error bar for the most part comprises 0, I'm not too worried about it. We're going to see when we get to regression, I believe we're going to see an example that is really clear, the pattern, and I think that's going to help you understand when, you may be violating some assumptions. So here again, it looks like they're independent. I don't see an increase in the spread of the data as you move from left to right. So there's not a indication of lack of homogeneity of variance. Also, I was telling you that we use the studentized or any form of normalized residuals, especially for checking the outliers, because then we can have that -3 and 3 thresholds to look at. So it doesn't seem like there's anything wrong here. This next plot is just a QQ plot for the error. So notice that the error does have 36 points in the residual because it is a residual for each one of your experimental units. Whereas the random effects had 1 for each level of that random effect. So only 4 for blocks and then 12 for block by potassium rate. So here again, a slight deviation on the tails of the distribution, but doesn't seem like it's something for us to worry too much. So I would say they look normal. If we do that density plot, same way. I mean, maybe the tails are a little bit higher than you would hope, but I don't think we're violating any assumptions here. All right, so then we got to this point where we ran the model, we ran the ANOVA. There was something significant there, meaning that we want to use this model for inference. We checked the assumptions of the model before we did inference, and the assumptions held. So now we can go ahead and extract model means and do pairwise comparisons. So I'm leaving you here the EM means code already for the nitrogen and potassium rates at the same level. So we're not, and perhaps here is a good point for us to talk a little bit about something. Because nitrogen is nested in potassium rate in the design, it does not mean that that's how you need to break down your interaction here, right? It does not mean you need to do this. You can still do everything at the same level. It's just that the error that's going to be pulled for different ways you make comparisons is going to be different. But you still have the freedom of looking to those means and pairwise comparisons in any way you want, especially for that two-way interaction that we talked about. That for a two-way, you have 3 ways of breaking down those means and doing pairwise comparisons. So I left you here, and we can just go ahead and run that. So here we're basically looking into no structure, right? So everything versus everything else. Now, what is interesting is that this standard error here is basically pulling different amounts of error from different parts of this model, especially because you're looking into that interaction. So the interaction here is basically mixing potassium and nitrogen and potassium rates, and we know that they're on their main effects, they have different errors testing them, therefore different standard errors as well. Something we can try very quickly is, let's say let's just look at this SE and the degrees of freedom associated with that SE for only nitrogen and only potassium. So, I'm getting off a little bit off what I planned for the class, but I just want to take some notes here. So let's say for this, we have SC of 330 and DF 22.9. Now, if I just do nitrogen rates, let's see how those are going to change. So if I just look at nitrogen rates, we get an SC of 209 and a degrees of freedom of 8.19. If we do just for potassium now, let's try that last one. we get an SC of 232 and DF of 8.28. So what is going on here is first we have a different error associated with depending how we extract our means. This does not happen. If you were to go back and check with our RCBD without a split plot, your errors would be the same. They would not be the same from RCBD fixed or random, but they would be the same within a model if you just check different components because they're all at the same level and structure. In this case here, we have a structure in place, meaning that the number of degrees of freedom that go into calculating an error and the error itself, where is it pulling the error from? Is it coming just from the residual? Is it coming just from the random effects? And what part of the random effects are contributing to that? Is it block or is it the nesting of whole plot and block? So that trade-off there is what we see on a split plot. And therefore, this error is changing depending on which level of these means you're extracting. So that's something that's different here on a split plot as well. Also, something that's kind of intriguing is you see this degree of freedom being like having a decimal point there. So what happens is when we use, so in lecture, we talked about a few different ways of estimating random effects. So one is just the ANOVA, which is what we were using with LM, although LM does not, only takes one variance component, which is the error itself. And then we have restricted maximum likelihood and maximum likelihood. When we're using REML or maximum likelihood for that matter, especially on these more complex designs where you start having nesting of errors, especially, and when you pull a mean or a comparison, that error that makes up that mean is coming from different parts of that design, it starts to become very difficult to calculate exact degrees of freedom. It's easy to calculate exact degrees of freedom if you don't have a lot of error structure in your model. But as you start adding error structure, that becomes more complicated. And therefore, we need an algorithm for that, like REML. And because of that, we don't have like the degrees of freedom now have a decimal point because it is an approximation of how many degrees of freedom are being used there by REML in this case. Yes, Selvin.
Yes, in this case, we have like the standard error is the same for all the combinations when we do like the interaction. But if we have unbalanced data, should we expect different standard errors for?
Yes, that's a great question. And that would happen really in any design. But if you have unbalanced data, you would expect to have different standard errors for different means. Yeah. Nice. So, well, I just want to go back here to the potassium rates and rates that we had originally. Rates, grams per hectare. Just wanted to show you how that error was changing because we have multiple error sources. Oh, I think I actually just I was not following or did not look down to see what I was showing you here. But basically these chunks are just to show you exactly what we did above, but for you to keep the code. So I'm just going to copy this. So this chunk here was just getting the means only for potassium and looking to the error. And then the next chunk, it was just for nitrogen. So that way you can keep the code as well. Don't have to delete it.
Like if you do one more split like potassium, yeah. So then the standard error will decrease, right? You would expect because it's a subplot.
Yeah, so that's a good point, Aman. So Aman is and perhaps I failed to point it out, right? So as we were expecting, the error associated with nitrogen is lower than the error associated with potassium, which is above here, right? So nitrogen, the standard error is 209, potassium is 232. That is just mostly because we have less degrees of freedom being used to calculate the error of the whole plot units than we have on the split plot units, right? So yeah, so absolutely, whatever is the smallest structure you have on your model or on your design is going to be the one with the most degrees of freedom in the error, and therefore smaller errors, higher chances of finding differences in your treatments. Yep. Okay, so I guess a few points I had here for us to discuss, and then I'll give you a 5-minute break. So so the standard, well, as we're seeing here, the standard error of the whole plot, which is our potassium rates, and our split plot, which is the nitrogen rates, are different. And this is expected because we have a split plot, we have that structure in place, we have different number of degrees of freedom in those errors and different errors for the different sizes of experimental units. If we were to do a same comparison on our previous exercise with RCBD only, they would all be the same because there's no structure in the error. Everything is getting the same error across the board. I guess we just talked about this with Amandeep's question, is that the standard error of the split plot treatment factor will always be lower than that from the whole plot treatment factor. The reason for that is just, again, because of how many observations are going into the error that then tests that factor. And if we were to go back to our ANOVA table, you will be able to see this again. Yes, Aman?
That phosphorus will have less error as compared to the other substance, you know?
Right. So Aman was asking if we had phosphorus there as well in that example that I made up with a split plot design. If the phosphorus was the split treatment factor, so we would have potassium, nitrogen, phosphorus. Then yeah, but phosphorus would have the most degrees of freedom overall, and therefore the most degrees of freedom in the air that tests for phosphorus, and therefore it would be the smallest standard error overall. All right, and so when we compare means, which is what we're going to do next, the error of those, well, the error associated with a comparison is actually being pulled from different components of this model. So some of the error is going to be coming from the random effects part of it. Some of the error is going to be coming from the residual variance from the model. So which did not happen. Well, I guess it happened on the RCBD random blocks, but it happened equally to all treatments. Here, it depends how you get those means, right? So in our case, we're getting all the means, everything versus everything else, like we just had here. And so all of these are getting the same error, but this error is inflated if you compare to getting if you just got for potassium, the error was 230. If you just got for nitrogen, the error was 209. So the combination of both of them gets you the largest error because you're pulling, that error is coming from different sources from your model, from the residual and from the random effects as well. Okay, so I'm gonna stop right here and give you a 5-minute break if you want. And then we can come back and finish this exercise. And I do have something to tell you afterwards as well. So. All right, let's resume here. So we determine how we are extracting those means. Again, the reason that I decided to do everything versus everything else, it was just, I mean, in this case here is really just an option, right? But you know that you could have gotten one inside of the other or the other inside of the one as well using the vertical bar. All right, so we can go ahead and get our pairwise comparisons. Just the same code as before. We're using no adjustment. We're reversing the order, so highest is better, and then assigning letters instead of numbers. If you just run that, we end up with these letters for those means. We've done this before, so this is nothing new to you. The next thing is we're just going to do some live wrangling just to be able to better plot. Same as we've done before, we turn this into a data frame. We extract just the letter by trimming the white space, and then we create treatment name that is just pasting the nitrogen plus the potassium rates. If you run that, you end up with this data frame here, where we have the means and then the letters and the treatment name. And then finally, we're going to do the final plot, which is the same as before, but we're going to check if the letters are the same as before. So I always like to show raw data when I can. So we're going to show raw data here using a box plot and then a statistical summary, which comes from our letter separation coming from the model, a statistical model summary with the letter separation from the model. I think I left you everything there already because we've done this, we've built this plot from zero before, so you should be familiar with what's going on. This is what we get, and then I'm gonna hit that GG save to export this. And I do want us to just take a quick moment to compare what happened with the letter separation between treating as a split plot and not as a split plot, just as a randomized complete block design. So I'm going to go here in my output and click on this plot that I just exported. So that is the plot for the split plot analysis. And then I'm going to navigate to my files here and go to our previous exercise, 04 RCBD. On the output, look at the RCBD mix means. So we already compared the RCBD fixed and random block, everything, right? That's what you did on the previous quiz, I believe. And we saw that there was no difference. And if you remember, the reason for that is because on a balanced randomized complete block design, even though the mean errors are different, but when you do pairwise comparisons, which is the result of, when you do pairwise comparisons to get a letter, so that even though we're showing a letter with a mean, but the letter is coming from pairwise comparisons. For pairwise comparisons, the random block extra error source cancels out and does not interfere in the error of the comparison. So just quickly summarizing that, we've seen before that the letter separation did not change between RCBD fixed block and RCBD random block because on the pairwise comparison, the error of the block cancels out. Now I want to compare our randomized complete block design with block as random, which was the last one we did, with what we did today, which is still a randomized complete block design with blocks as random, but with a split plot on top of it, meaning that now we have another source of error besides just the block and the residual. We have the potassium rate as well. So let's see if the letter separation changed between those two. Let's see, I'm going to keep the RCBD mix on top, and I'll bring the RCBD mix split plot on the bottom. Maybe we can kind of eyeball to some extent. So it's still the highest treatment, is still this, I mean, there's still A just by itself. We have an AB, a CD here. So it seems like on the split plot, which is on the bottom here, we don't have E's anymore. The lowest is a D, meaning that some of the letter separation changed. You know, so I mean, perhaps somewhat our interpretation of some of these comparisons have changed, right? So, you know, for instance, let's see here. So this has a D. Well, this has letter D. This also has letter D. So these are not different. And this also has letter D. So these three are not different. And before they had the letter E, so that interpretation didn't change. Let's see what else, if there's something else that may have changed our interpretation. So this was ABC, and there was a C there. This is AB. Yeah, so maybe one difference I'm seeing here is, so I'm just gonna be pointing if you want to look at my screen. So this was ABC, and this was CDE. So because they share the same letter, they were not different before. Now this is AB, and this is CD. So they do not share the same letter. So now they are different. They were not different before. So some interpretations have changed. And again, you would not do this, right? You would not run the same data in what you did on the field using different designs on the computer just because you want to play with it. But this is just for us to see, okay, things are changing. In this case here is because the split plot has a different error structure altogether compared to just an RCBD without that split plot structure. And that impacts your errors depending if you're looking into your whole plot or a split plot treatment factor. And that impacts your pairwise comparisons as well. All right, any questions about these points?
How this changed?
You mean, so are you looking at one plot specifically? So your question is why the letters change between one and the other?
The data frame.
So this one I have on top is for the RCBD mix. So the one that we did last exercise. So the one that we did today is the one on the bottom here, on my screen at least. So the one that we did today, there's no E there, but the one that we did without the split plot, just the RCBD with blocks random, had an E, which is the one on top. At least I had. I don't know. Yeah. Yeah, so that goes back to, I mean, you know, I think I mentioned, I guess, in words, but if we were to visualize it, we can go back to a lecture, which I think is this one here. So if we just look at that ANOVA table, that's going to help us understand why. So potassium, the effect of potassium is being tested with the mean square of the whole plot error, which is this one here. And in our example, the whole plot error has 6 degrees of freedom. The effect of nitrogen rate and potassium rate are being tested with the mean squares of the split plot error, which is here, and it has 18 degrees of freedom. So the more degrees of freedom you have in the error, the more certainty you're going to have about anything that you're testing here. So we want to have more degrees of freedom in the error. Of course, that is to say we want to plan for more degrees of freedom in the error. I don't want to say we want to have, so you don't get the idea of like, well, easy for me to have more degrees of freedom in the error. I just run as an RCBD without a split plot, right? That's not what I'm trying to say. I mean, we should aim to plan and design a study that has enough degrees of freedom of the error, therefore that has enough power for us to find differences and that accommodates sources of variation in our study. So if you need an RCBD, you run an RCBD, you may consume, I mean, you will consume degrees of freedom to calculate the block effect, but hopefully that block is helping you beyond that consumption of 3 degrees of freedom in our case to explain more of the variability on the block and remove that variability from your treatments. So I guess we had this conversation before, but yeah, overall, well, Priscilla, to get to return to your question, we have different errors because both the sum of squares of these errors are being separated now, right? So we have this error and we have this error and also the block error associated with the whole plot because this is the interaction. So we have different amounts of variability in different errors and also different number of degrees of freedom in different errors. And in general terms, the more degrees of freedom you have, the more power you have to find treatment differences. And before, if we were to go back to this ANOVA table for the randomized complete block design without a split plot, you would see that this denominator mean squares, which is the error that we use on the F ratio. This would be the same for potassium, nitrogen, and the interaction. In a split plot, they're not the same because you have that structure. All right, any other questions about what we just saw? All right, so I have a quiz for you. Let's see if you have more questions. No, I'm kidding. That's not the goal. I just want to make sure that we're following along. But today, I'm trying to incorporate some new things in the way that I assess you. And so today I want your quiz to be with your neighbor as well. So really, like if it doesn't have to be with the person that's right next to you. If you wanted to walk around and work with somebody else, you could. But it's just working with someone else. If you're online, you're gonna have to work. Oh, you know what? Well, let me try something very quickly here. I don't want to take a lot of class time, but I was told you can do breakout rooms. And I never tried that. So let me see if I can easily try.
Excuse me, Professor.
Mm-hmm.
I'm not sure if we have already talked about it, but because I joined the class at 9:32 today. Have you discussed the midterm? You asked me to remind you again on Tuesday.
Not yet. We'll get to that after the quiz.
Okay.
So I'm gonna for those of you online, I really don't know what's the best way, and I'm gonna do this. I'm gonna let you all choose a room. If you are in Tifton in the classroom, you don't have to choose a room because you already have 3 people there. If you are by yourself attending from your office, then choose a room where you have one person. Like don't all go into the same room. Just choose a room and then I'll give 5 minutes. And before I assign you to those groups, I just want to make the quiz public. So my goal here is that you all, like you can talk with your neighbor, you can, talk about what each one of you think is the right answer. In the end, each one of you have to answer separately. So make sure each one of you submit your answer separately, but you can talk with your neighbor to see what you all think of it. So before I make the breakout rooms, let me just make the quiz visible. Okay, so I made it visible. Let's see, let me see how many people we have online.
Yeah.
I'm gonna create 5 breakout rooms. If there's more than needed, then that's fine. If you need, if there's less than needed, then you can go into a group with 3 people. But the goal is just that you talk with your neighbors about what I'm asking. So I'm gonna create the breakout rooms. If you're online, please choose one with another person. And then I'll give you 5 minutes. And I think I'm gonna be able to talk to you when you're there. I'm not sure. We'll see what happens. All right. I'm just gonna open all rooms. Okay, yeah, I think all rooms are open. So if you're online, just choose a room with another person. If you are in person, go ahead and work with your neighbor on this quiz. and I'm going to give you maybe 6 minutes just for you to have a chat. All right, so make sure you submit your answers. I'm not looking at them yet, but I do wanna, well, you need to submit before we start talking though. So I'm gonna give you 30 seconds to hit the submit button. If you don't, I'm gonna close the quiz and you're gonna be not gonna be able to complete it, unfortunately, but we have to move on. So 30 seconds. And then we're gonna talk about it. So again, make sure you submit before the 30 seconds, otherwise I'm closing and I'm not gonna be able to make an exception. Oh, yeah, that's not what I want. 30 seconds. All right, so you got another time extra. All right, so make sure you submit, and then I'm gonna close the quiz and we're gonna talk about it. All right, I got 14 answers. All right, I'm closing the quiz. Oh, don't know if those. I don't know if people were able to see me or to hear me on the breakout rooms, right? Yeah, all right, so we'll give them another minute, I guess.
I think if you close the breakout room, I'll come back. I think.
Yeah, I close and it says, we'll close in 32 seconds. Five more. That's right. Oh, yeah.
Dr. Bessos, do you have more time?
No, so I'm learning about breakout rooms as well, and I just noticed that I was giving you all these warnings and you were not hearing me.
Even I was in the room with Ashbin, I could not hear Ashbin. I don't know why. So
Well, maybe Ashwin was not there, I guess. Or I'm not sure what happened, but really what we're gonna do here is if you were in the breakout room and you did not hear me give like 30 seconds extra time to submit, just make sure you submit in the next 10 seconds. Because we need to move on and I don't want to keep you later. But
I think, at least they can see it.
yeah. You mean putting on the timer here, 10 seconds? All right, 10 seconds, everyone. Submit it, and if you don't submit, I'm closing it, and you're not getting your grade for it, unfortunately. So,
Only one left. I think maybe someone has it.
all right. So I'm gonna close it. And oh, can you close on your side, Arminder, just so I can keep moving here? Can you close it on your side? Okay. And then we're gonna keep moving here. So no one. Okay. So what did you, if somebody want to share with me some thoughts of what you answered on that first question. So what is the main difference in the model function between a split plot in an RCBD versus an RCBD? Okay. That is a difference in the model for, I mean, yeah, in the way that we write the model for sure. That's not what I was thinking as what I was getting, but that is it's a good one that I was, yeah. Yes, Carlos.
Instead about the actual RCBD versus the RCBD or evidence for error.
Mhm.
It's the same for RCBD.
But so I guess and maybe, and again, these are like, the quizzes I'm very lenient on them, so I'm not looking for, unless you told me something completely wrong, then you may not get the answer, but, so for example, the function is something I was not thinking, but it is definitely a difference. What I was thinking more was like, if you think when you write the code of the model, what is the difference between setting an RCBD and setting a split plot in an RCBD?
Is the nesting?
Yeah.
Sorry, go ahead, anyone online.
Like, is it the nesting thing like the block? The whole plot is nested inside the block.
Yes,
Yeah.
yes, absolutely. Thanks, Ashwin. Yeah, I think that was what I was originally looking for in here, but if you said something that makes sense and that is not wrong, then I'm taking any of those. Anyone else? I mean, so Amandeep said the function, Ashwin and maybe others were saying the nesting. Anyone else wrote something else?
The error comes from like the two part for for the split plot, one from the whole plot and one from the split plot, and for the um, only the RCBD, it's the whole plot and the random effect.
Yep, perfect. Yeah, that's not something that, I mean, I guess as far as the code itself, I think would be the function and the nesting of the error. But then, yeah, behind the scenes, there's a lot of different things going on. All right, so anyone else that has not shared yet would like to tell me, perhaps if you look here on this first one, what would that be? Where would number one go here? This is CRD, right? How do you know?
No.
It doesn't have the rep. What else? The function, right? So we know that we know this only has one error source, which is the residual, because we're using LM, and therefore CRD is the only design that we talked about up until now. Well, not the only one, yeah, but it's the simplest one where it only has one error source. So yeah, this would be CRD, right? So this would be number one. Somebody else want to tell me about this one? What is this? Shay, what do you think?
Oh, it's just it's RCBD with block treated as fixed effect.
Right. And how do you know that?
It's LM and rep is not a random effect in the model.
Right. So this would be a block RCBD with block as fixed, right? So let's see. Blocks, yeah, so this would be number two. Let me go online and see if someone can help me. What about in Tifton? What do you guys think is the next one? If you're saying something, I can't hear you.
In this case, like replication is treated as a random effect, right? The RCBD complete. This is the RCBD with block treated as a random effect.
That's right, Ashwin. So this would be number three, would be here. And then obviously the last one is what is left, but perhaps if someone else, so either Polly or Ali or anyone else in Tifton, I think you were going to say something. How would you know that this is that? Like if you did not have only one option left, how would you know that this was that?
The function LMER,
Mm-hmm.
and also the interaction between those two, and also being K rate being nested under the block
as a random effect, right? Yeah. Perfect. All right. Yeah, that was it for the quiz. Again, I'm just trying to see if you're following along in class. I know we're talking about different designs. and we just have 1 more minute. So let me do this. Let me ask you to first come to your script, save it if you have not saved yet, and then go to your Git pane. You're gonna stage, you can just stage the script if you want. I also have the data because I added.
Excuse me, Professor.
Yes.
Can I ask a real quick question?
Can you just wait
So-
until I finish this part and then we'll come back to you, Omar?
Yeah,
Just
of
so
course.
we don't break the flow. So if you stage there, then click on that checkbox icon. You just can say finished SPP or whatever you want. You can commit, close, and push. And if you want to make sure that what you did is reflected on your GitHub, if it all worked, then you can go on your own GitHub and check if those changes you made to the script are reflected. All right, so Omar, I'll be with you in a second. I just want to say we are at 11:10. So if you have answered the quiz, I guess you don't have another option at this point. If you have did the git push until git push here and claim your attendance on issues, then you're good to go. You're dismissed. I'm going to stick around for another few minutes here in case anyone has any questions. And thanks, everyone.